Hi, my name is Natalia de Souza, and today my group will be presenting on the thermodynamic applications on the ISS. After a brief introduction, I will be discussing the air revitalization system.
I'm Mizuki Small, and I will be discussing heating and cooling.
I'm Ria Kuroka, and I will be talking about water recovery. So the International Space Station, the ISS, is a collaborative space habitat in low Earth orbit used by scientists to perform experiments that help us improve life on Earth and prepare for a more complex future space travel.
Our group will be discussing a few of the environmental control and life support systems, ECLSS, on the ISS and their thermodynamic applications.
Today, I'll be discussing the air revitalization system. Air revitalization is the process by which air on the ISS is recycled. This includes removing CO2 from the air, filtering out contaminants, and monitoring air quality and content. Today, I'll discuss CO2 scrubbing, which is the chemical process by which excess carbon dioxide is manually removed from the atmosphere using the carbon dioxide removal assembly, or CDRA. You can see the CDRA up here superimposed over an image of the ISS floating over the Earth. So how does the CDRA work? First, air from the cabin of the ISS is pulled into sorbent beds composed of either a molecular sieve or an amine, where CO2 is filtered out. This scrubbed air is then recycled back into the cabin. A second unit, meanwhile, is full of CO2. This unit is directly next to the first and is completely cut off from the cabin air. This unit gets partially heated by reactions in the active absorbing unit, as well as by electrical heat created by the solar panels on the ISS. Finally, the CO2 from the second unit is dumped overboard into the vacuum of space. Once this process is completed, the beds are regenerated upon exposure to heat and the vacuum of space and will cycle jobs. Here's an image of the cycling CO2 removal systems using molecular sieves and amines. As mentioned before, air from the cabin goes into this first unit where the CO2 is removed and the scrubbed air returns to the cabin. Meanwhile, the heat from this first unit heats up the second unit, which takes a full tank of CO2 and dumps it back into the vacuum of space. Once one cycle is completed, these two units will basically swap jobs. So now air from the cabin will enter the second unit, get cleaned from CO2, and then return to the cabin, while this unit, which is full of CO2, will be dumped into the vacuum of space with the help of heat from the second unit. So what is the relevance to thermodynamics? Well, air revitalization has a lot to do with the first law of thermodynamics. This law states that energy cannot be created nor destroyed. Chemical energy from separating the CO2 molecules is converted to heat energy, which then warms up the second CDRA unit and aids in the release of gas into the vacuum of outer space.
Now I'm going to be talking about heating and cooling on the ISS. Temperature control is very important because it keeps the temperature inside the ISS at a habitable level. Without it, the side facing the sun could reach temperatures up to 250 degrees Fahrenheit, while the other side could reach temperatures down to negative 250 degrees Fahrenheit. To combat this issue, engineers use insulation to keep heat in and keep solar radiation and cold out. They use multi-layer insulation, which is made out of mylar and dacron. The mylar works to keep the solar radiation out, while the dacron separates the mylar sheets so that heat will not be conducted between them. But one of the problems with insulation is that because of the first law of thermodynamics, which states that energy cannot be created or destroyed, all the heat that is generated from the electronics and other systems on board the ISS has nowhere to go. That is why there is also a system called the Active Thermal Control System, or ATCS, which removes this heat from inside the ISS so the astronaut won't overheat. According to a report from Boeing, an ATCS uses a mechanically pumped fluid in closed-loop circuits to perform three functions: heat collection, heat transportation, and heat rejection. The active thermal control system consists of four systems, which includes the internal active thermal system, IATCS, and the external active thermal control system, EATCS. The IACTS uses cold plates and heat exchangers, which are cooled with 2 loops of water to collect excess heat and transport it to the outside. This system circulates through the interior of the US Destiny laboratory module. The IACTS uses water because it is safer than ammonia, which is what the EATCS uses. The external active thermal control system uses 2 loops of ammonia and large radiators located outside of the ISS to cool, acquire, transport, and reject excess heat from all modules on the ISS except for the Russian modules. The EATCS is the primary active heat rejection system on the ISS, and it has the capacity to reject up to 70 kilowatts of heat per loop. Here is a diagram of some of its components. You can see the radiators near the back and the ammonia tank on the left. All systems utilize 2 loops so that if one fails, the system will still be able to run. So using a combination of insulation and an efficient liquid heat exchange system, the ISS is able to overcome the limitations of the first law of thermodynamics and keep the temperature inside the ISS at a habitable level.
Now I will be talking about water recovery on the ISS. Simply put, water recovery is the process of taking contaminated water, ridding it of all of its contaminants to get clean water that can then be put back into the storage tank to be reused. The ISS's water recovery system, also known as WRS, consists of 2 parts, the urine processor assembly and the water processor assembly. The 2 pictures on this slide, the one on the left is showing the urine processor assembly flight experiment, and then the one on the right is showing the water processor flight experiment. The urine processor assembly, also known as the UPA, uses a lower pressure vacuum distillation process that removes the water from the urine. This entire assembly is actually rotating, which helps compensate for the lack of gravity in the ISS and helps in the separation of liquids and gases. After the water is fully processed here, it gets sent to the next part along with the rest of the wastewater. But now the question is, what is low pressure vacuum distillation? So to break it down, distillation is the process of purifying a liquid through a series of converting the liquid into a vapor and then back into a liquid again. It's used to separate liquids from solids or liquids with different boiling points. Vacuum distillation is the same process, it's just done at a lower pressure, which means that the liquid is able to boil at a lower temperature. This is useful when the ambient pressure doesn't allow for the standard distillation process, or if you just want to speed things up. On top of this, the entire assembly is rotating, so there are multiple parts that help the process work, even without gravity. This is where thermodynamics comes in. The low pressure vacuum distillation process uses a combination of heat transfer work and pressure to its advantage to effectively purify a liquid by separating the contaminants from the water. After all of this, the water from the UPA gets sent to the water processor assembly, also known as the WPA, along with the rest of the wastewater. From here, the WPA removes free gas and solid materials, air and lit, before sending water through a series of multi-filtration beds. After that, any remaining contaminants are removed by high temperature catalytic reactor assembly, which to my understanding is a process to kill microorganisms by means of a chemical reaction. And as a final step, the resulting water is checked by electrical conductivity sensors. Unacceptable water is reprocessed, clean water sent to the storage tank for the ISS crew to use later.
Thank you so much for following along with our presentation about thermodynamic applications on the ISS. We hope you learned a little bit about how we keep astronauts alive using the environmental control and life support systems there. And to close off, here's an image of the expedition crew number 65, which is the current crew up on the ISS. Thank you so much.